Hey guys, welcome back. Today we're going to talk about some systems of equations that don't work out the same way that most usually do. So, for a system of equations, there's really three different things that can happen. First of all, and this is what we've studied most of the time, the equations have one unique solution, one pair of numbers or triplet of numbers if it's a bigger system. That makes it true and no other pairs work. There are two other scenarios that could happen. One thing that can happen is that the systems actually have no solution, that there is no pair of numbers that makes them true. And alternatively, it's possible to have lots of different solutions. So let's look at a system that has no solutions and see what happens when we try to solve it using our three techniques. So let's start by solving this system by graphing. And if you need a reminder what those steps are, here you can look and see. Press pause and write them down if you have to, but we'll keep going. To solve a system by graphing, we will immediately start by graphing both of these. And so 3x plus 2 starts at 2. And then the slope of 3, so I'll go from there up 3, and up there up 3 again, and do a few more down 3 and backwards and so forth, and try to draw in a line as best I can here. So there's our first equation. And for this other equation, we could quickly find some points. If I plug in a 0 for x, I get that y has to be a negative 3. And if I plug in a 0 for y, I get that x has to be a 1. And so I can plot those points. Negative 3, or 0, negative 3 is this point down here, and 1, 0 is here. And if I continue this pattern, I'll go up 1 and over 3, up 1 and over 3, up 1 and over 3, and so forth. If I draw in this line, I see something different happening than I've seen before. These two lines don't appear to cross. And in fact, if we look very carefully, they both have the exact same slope. They both go up they both go up 3 every time we go over 1. And so if they both continue to do that forever and ever, they won't ever cross. They're what we call parallel. And if they don't cross, well, where's the intersection? There isn't one. And so, well, that's why these particular systems are unique. So the answer to this, when it says to solve, is that there is no solution. So that's what you would write, no solution. Sometimes it's helpful to write that these are parallel lines. And that's it. There's a word for this type of system. A system like this where the two equations are never equal is sometimes called an inconsistent system. So write that word down, inconsistent, and if you ever see or hear that word from your textbook perhaps, that's what it's referring to, these equations that don't ever intersect and therefore there's no solution. So here's the exact same system again, and this time we will solve it by using substitution. Again, for those of you who need a reminder what those steps were, you can write them down quick. And let's get started. We will probably take this 3x plus 2 and write it in for the y over here. This is a nice one to use substitution on because you already got y by itself. So that gives us 6x minus 2 times 3x plus 2. And that equals 6. If we use the distributive property, like we usually do, that gives us negative 6x and a 2, and over here a 6x drops down, and 6, and 6x and negative 6x, they can cancel out. You've been eliminated. Wait a minute, that's not this particular That's the substitution. Wait a minute. Where's our variables? 2 equals 6. That doesn't make sense, although I think you may have seen something like this before. If you remember back when we solved single variable equations, we used to call this a contradiction and say that there's no solution. While we wouldn't call it a contradiction, the end result is the same. If you are working on a system and you end up with no variables and a false statement like this, 2 equals 6, well, that's a clue that there is no solution. So let's try elimination. And again, for those of you who need a reminder how the elimination method works, you can write those steps down. The first thing I'll have to do is line everything up. This has not been done. This is not a good one to use elimination on, honestly, but we'll rewrite things. These 3 x's should be on this side, and so if they're going to be over there, they're going to switch signs. So it would be negative 3 x's and still a positive y equals, and the 2 is still on the same side, so it doesn't change sign. And now I need to create an opposite, and I see 6 x's. If this was negative 6 x's, that would work. So a quick multiplying by 2 should create opposite x's. And if we do that, let's quick copy this one over, 6x minus 2y equals 6. And if we do this multiplication, 2 times negative 3 is negative 6 x's. 2 times y is positive 2y's. And 2 times 2 is 4. And when I add these 2 equations together, the x's, you've been eliminated. The y's have also been eliminated. And wait, that's weird. There's nothing left over there. Well, there is. There'd be 0 left. And then on this side, 6 plus 4, that adds up to 10. And again, we get this weird scenario where there's no variable, and we get a false statement, 0 equals 10. That is our clue that there is no solution. So there's an example of an inconsistent system and how we can find it using all 3 different methods. Let's look at another special system now. It looks, I don't know, looks like a normal system, but when we graph these, you'll find something unique happening. So why don't we get started? This first one here is probably a good one to use the zeros method again. If I plug in a 0 for x, then y has to be a 2 to make it true. And if I plug in a 0 for the y, then x would have to equal 6 to make that true. So I can plot those points. 0, 2 is this point right here, and 6, 0 is over here. I can connect those. I can also find that halfway in between them would be another pretty point, and so forth. So try to draw that as neat as I can. And there's our first line. For our next one, this is not a clean one to use the zeros method on quite as easily, so maybe I'll try to rewrite it in y equals form. That's not so bad. I can subtract 2/3 x from both sides. That gives us 2y is equal to negative 2x over 3 plus 4, goodness. And we need to divide everything by 2. This divided by 2 is nice. This divided by 2 is a little ugly. It's the same thing as if we put a 2 in the denominator down here. Let's see, we get y equals, and negative 2 over 6 reduces to 2 sixths is 1/3, so negative 1/3 x. And then here, 4 divided by 2 is a 2. And if we were to graph this then, we would begin at 2, so kind of the same starting point, and then the slope is down 1 over 3, and so from here we go down 1 and over 3. Looks like we're going to be the exact same line. So my question then is, where did these lines intersect? And I didn't draw them precisely, but if I had, you would see that they're intersecting everywhere. They're intersecting, of course, at 0, 2, where we started, but they're intersecting here and 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 here. What answer could we write? So the scenario here is another example of a strange system, and the answer to this is that there are infinitely many solutions, and that's what's usually written. There are infinitely many solutions. There's too many for us to list them all, and so we're not going to try. Essentially, this system of 2 equations is really just one equation. It's the same equation, just kind of rewritten in a different form. Let's look at the same system and solve it this time by substitution. So, if I look at this first equation, I see an x that's not too hard to get by itself, so that's how we'll proceed. Subtract 3y's from both sides, and x equals 6 minus 3y. Then we'll make our substitution over here. So 2x over 3 is the same thing as 2/3 x. So I'll write 2/3 times 6 minus 3y plus 2y equals 4. And 2/3 of 6 is the number 4. 2/3 of 3 is 2, and that's a negative, so minus 2y. And then there was this plus 2y over here, and I get 4. And if I combine the y's together, they cancel themselves out, similar to what happened last time. In fact, we don't have any variables left over, and we have this time a true statement as opposed to the false statement we had last time. And that, when we lose our variables and we have a true statement, is our clue that these two equations are identical, that they are the same. And if that reminds you of the identities that we studied earlier in the year, well, good, they should. So again, we would say that there are infinitely many solutions. We'll do one more. We'll look at the same system, this time with elimination, and you can probably anticipate what's going to happen. In order to create an opposite, I might multiply this bottom equation by 3. That will have the convenience of getting rid of this fraction, but that'll make this a 6y. And if I can multiply the top equation to get negative 6y, that's easy enough if I multiply by negative 2. So let's proceed with those multiplications. On top, I get negative 2x. Negative 2 times 3 is negative 6y, and negative 2 times 6 is negative 12. And then on the bottom, 3 times the fraction of 2 over 3. The 3 and the 3 cancel themselves out, and all that's left is 2x. 3 times 2y is 6y, and 3 times 4 is 12. And when I add these equations together, it's like an atomic bomb blew off. The entire thing, everything has been eliminated. The x's cancel, the y's cancel, so I'm left with nothing, and even the numbers cancel this time. 0 equals 0. Again, variables are all gone, and a true statement, that is our clue that an identity, or in this case, identical equations have happened. So we would again say that there are infinitely many solutions. So, to summarize, here are the 3 different scenarios and the sorts of things that can happen. Typically, when we use the graphing method, we see intersecting lines, and we find the solution by looking where they cross. And if you're trying to use the substitution or the elimination method, you go and you find the variable, you find the value for one variable, and then you plug that back in and you find the variable, the other variable. And you plug that back in and you find the value for the other variable. So with these two types of special systems, when you graph them, this is when you find parallel lines showing up, and parallel lines never cross, therefore there's no solution. And if you're trying to use one of the algebraic methods, you'll find that your variables disappear and you end up with a false statement. That means your two equations can never meet, and we say that they're inconsistent, or sometimes we say that they're contradicting equations. They can't both be true at the same time. It's impossible. And when you have a situation where there are many solutions, then your graph ends up being one line and the same line right on top of it. So it looks like there's just one line. Since the answers are the solutions, and there are solutions all over the place, anywhere where those lines are on top of each other, we say that there are infinitely many solutions because we couldn't possibly count them all or list them all. And then if you tried to solve that system using an algebraic method, again, you'd find your variables disappear, but this time you have a true statement. And that is our clue that, like identities, we have identical equations. So, thanks for listening, and there's an explanation of some special systems. Be on the lookout for those from every assignment and quiz and test from here on out. They won't be specially labeled. They might show up, and so you have to tackle each one as if it's a normal problem, but keep in mind the clues that I've shown you here when something goes wrong.